Welcome to our brand new explainer. Today we're going to decode the massive, invisible networks that are, quite literally, shaping our entire future. We're so used to just looking at the physical world right in front of us, the stuff we can touch. But the true revolution, it's happening right now, both miles above our heads and deep inside digital servers. So let's dive right in.
We're kicking things off with a number that is honestly kind of hard to even wrap your head around. $1.1 trillion. In recent valuation stages, this is the astronomical paper figure Elon Musk's wealth hit, essentially making him the first guy in the Trillionaire club. To put that into perspective, that's roughly the entire GDP of Switzerland. But what's truly fascinating to me isn't the money itself. It's what this empire is actually built on. It really comes down to two foundational pillars of technology: connecting the entire globe and fundamentally understanding reality itself.
Okay, let's start with that first pillar in Section 1, Starlink, the space flashlight.
So traditional space internet relies on these massive geostationary satellites just hanging out at an incredible 36,000 kilometers up. A signal has to travel all the way up there and all the way back. It takes forever in digital time. But Starlink satellites? They sit in low Earth orbit at just 550 kilometers. Because that distance is just drastically smaller, the ping, the time it takes for data to travel, drops to almost nothing compared to legacy space tech. It's a real game changer.
And we're not just talking about a couple of satellites up there. The sheer scale of this operation is absolutely staggering. Right now, thousands of these devices are zooming around the Earth at roughly 25 times the speed of sound. They are literally weaving a high-speed web around the entire planet as we speak. But how do they actually get that internet down to us? Well, Elon Musk gave this brilliantly simple analogy. Imagine one of these satellites is just a pocket flashlight shining down on the Earth. That beam of light forms a cone, right? And it covers a wide but completely fixed area of the ground below.
Let's play with that flashlight analogy a bit more, because the physics here are pretty unforgiving. A beam of internet coming from 550 kilometers away simply cannot compete with a cell tower that's, say, 1 kilometer away in downtown Manhattan. In a super dense city, with millions of smartphones pulling data, that wide satellite beam gets instantly overloaded. And that is exactly why Starlink and ground networks are perfectly complementary. In places where cell towers are too expensive or literally impossible to build, like dense forests, mountains, or really sparse rural areas, the Starlink cosmic flashlight works flawlessly. It eliminates the exact spots that traditional cables just can't reach.
But here's a thought. How do these satellites talk to each other if there's no ground station directly below them? Enter the laser mesh. Starlink satellites are actually linked together using invisible laser beams. It's basically like laying down indestructible fiber optic cables that just float in the vacuum of space, beaming massive amounts of data from one satellite to the next, right over our heads. And guys, this provides absolute global resilience. For example, when those underwater fiber cables were completely severed in the Red Sea recently, the Starlink network kept right on running without a single hiccup, just routing data through space instead. During earthquakes, floods, wildfires, when ground infrastructure is completely wiped out, this space web remains perfectly intact. Plus, they routinely drop paywalls in disaster zones, handing out free connectivity when people literally need it most for survival. It's incredible.
All right, let's bring it back down to Earth for Section 2, Neural Networks, the author at work.
Now, removing from the macro hardware network in space, down into the micro-digital network of the mind, artificial intelligence. The fundamental mechanic of most text-based AI, large language models, is simply predicting the very next word, or token. But there is a massive engineering trap here, and it's called token drift. Imagine stacking slightly crooked blocks. Every tiny prediction error layers right on top of the previous one. Over a long paragraph or essay, those little errors compound. The AI starts hallucinating, and eventually it just spits out total nonsense.
So how in the world do you fix that? Well, to prevent this drift, you have to make the AI act exactly like a human author writing a book. First, it writes a rough draft. Then it steps back to look at the gestalt, the big picture, the entire structural flow from beginning to end. Finally, it goes back and revises everything to ensure strict logical coherence. It's this exact process of constant big-picture revision that keeps the AI's train of thought from just wandering off a cliff.
Okay, moving on to Section 3. Real-world AI, photons on the input.
We've covered text, but what about AI operating out in the messy physical world?
Think of Tesla's self-driving cars or their Optimus robots. The wildest thing here is that these systems are never actually programmed to read a stop sign. Nobody is typing out the code, hey, if you see a red octagon, hit the brakes. Instead, they use something called end-to-end learning. They organically figure out the complex rules of reality purely by watching just colossal amounts of video data. They observe, and they learn the rules themselves.
And there's a brilliant biological analogy here because it's exactly how you and I work. Think about it. Photons of light hit our eyes. Our brain processes that raw input and then sends motor commands out to our hands or our mouth. Digital AI functioning in the real world is wired the exact same way. Video feeds straight into camera eyes, passes through the neural network brain, and translates directly into motor commands for a car's steering wheel or a robot's physical limbs. Photons in, controls out. Simple as that.
Which brings us to our final hurdle. Section 4. The limit of efficiency.
As we build these digital brains, we inevitably slam into the ultimate physical bottleneck of our universe: power and efficiency. Just look at this staggering contrast. Higher human brain functions, all of your complex reasoning, your memories, your creativity, operate on roughly 10 watts of power. 10 watts! That is literally a dim light bulb. To mimic even a fraction of that intelligence, a modern AI GPU cluster needs a monstrous 10 megawatts. That's a difference of 6 orders of magnitude. It really highlights how AI right now relies on sheer massive brute force calculation, while our biology, it remains the absolute gold standard for efficiency.
Scaling up these gigantic 10-megawatt server farms hits very real physical walls. The tech industry has already panicked over silicon chip shortages, right? Well, now they're facing a completely different problem. They are literally running out of physical electrical voltage transformers just to plug these massive facilities in. Because of this, the entire AI industry has had to pivot. They are now laser-focused on one ultimate goal: maximizing the amount of useful compute they can squeeze out of every single watt of energy. So these systems, from invisible laser webs floating up in space to neural brains learning directly from real-world video, they are advancing at just a breakneck pace. And it leaves us with a pretty wild question. If this 10-megawatt digital brain eventually comes to fully, deeply understand the intricate rules of reality, well, where does that leave our incredible, hyper-efficient 10-watt human minds? Are we destined to just be the creators, or are we going to end up being the observers? It's definitely something to chew on. Thank you so much for exploring this with me today, and I'll see you in the next explainer.